All right, so first we're going to talk about C13 NMR. And again, what NMR is nuclear magnetic resonance. And so that's the NMR. And so this is the same technology they use in MRI machines, where MRI stands for magnetic resonance imaging. They actually they took the word nuclear out of there just because people don't like that term. So for C13 NMR, what this is going to be telling us is in our structure, in our molecule, it's going to give us information about the carbons. And so you can kind of follow along with your handout worksheet. So the top is going to be talking about the different things that we get from the C13 NMR. So these are like different pieces of information for our structure solving. And I'm going to go through all of these and kind of use some examples. And then in addition, the first thing we're going to talk about are the environment. And so the different chemical shifts, or the ppms. And so that's kind of in this table here. So this first page of your handout is talking about carbon NMR. And then the bottom part we'll get to in part 2, that's going to be the HNMR stuff. So for now, we're just looking at carbon NMR. And so the first thing we're going to talk about at the top of that sheet is the environment. So the environment of the carbons. And so what this means, what it's telling us is what is attached to the carbons. Okay, and so that just means if we look at a carbon in our structure, it's going to give us some information about what's attached to it. And so in an NMR spectrum, it generally runs for carbon 13 NMR. It's running usually from a scale of 0 to 200. And these units are in a unit called ppm. And that stands for parts per million, but it's kind of just a random arbitrary unit that they use to just kind of show the different regions. So the numbers don't really mean anything specific, but it's where they are on the spectrum that tells us kind of what's attached. And so some terms that you need to know associated with this is that over on the left side of the spectrum, we call that downfield. And so the more downfield you are, the more left you are. And then to the right, we call that area upfield. So the more to the right you go, the more upfield you are. And so we're also going to be talking about shielding in just a second. So anything that is shielded, if a carbon is shielded, it's going to appear more upfield the more shielded it is. And the more de-shielded it is, the farther to the left it will be. So again, it's a spectrum. It'll be somewhere in this spectrum depending on how shielded or de-shielded it is. So that will put it more upfield, so more to the right, or more downfield, which means more to the left. Okay, so I'm going to kind of use an analogy to talk about the shielding. And so I like to think about it kind of like we're all the carbon atoms, and we're trying to climb this hill, up the hill. So up is to the right, so we're going up and to the right. And at the top of the hill is the magnet from the magnetic resonance, right? So there's a magnet up here that's kind of beaming down on us carbons as we go up this hill. And if we're heavily shielded, if we have a good shield, we're actually going to be making it pretty far up this hill, upfield. However, if we don't have a shield, the magnet's just going to hit us and it's going to knock us downfield. So we're going to get knocked down to the left side of the spectrum if we don't have a good shield on us. Okay, and we'll talk about what that means, what the shielding actually is. Okay. Okay, so what makes a good shield? One thing that is a good shield are carbons. So carbons themselves are good at shielding. Okay, and so we're gonna kind of break down that same region from 200 to 0. And so similar to what we did with IR, we're going to kind of talk about what stuff shows up in these different regions. And again, you can follow along with your handout. So this table is going to kind of show you the same sorts of regions that I'm going to go through. But again, you don't want to focus on memorizing the numbers exactly because stuff can show up outside of those regions depending on what's on the molecule. But you kind of want to know what stuff shows up where, generally, similar to what we did for IR. Okay, so anyway, I'm going to start in the downfield area. And so down around 0, and again, these units are in what we call ppm. And these numbers measure what we call the chemical shift. So the chemical shift is kind of where it is on the spectrum. And so here, kind of in the most upfield area, this is going to be the stuff with the best shielding. So in the roughly 30 to 10 kind of ppm region, so like here, this is what we call the alkyl region. And this is where you're just going to get kind of normal sp3 carbons that are just kind of bonded to other carbons. So again, what we're talking about, you're going to see a peak here for this carbon specifically, and then what it's bonded to is just other sp3 carbons or other carbons. Okay, so those will show up, these carbons will show up roughly in the 30 to 10 region in the carbon NMR. So then we start adding stuff. If we add stuff other than carbons to this guy, then it's going to start pulling its shield away. And so the first thing that can pull its shield off are just electronegative atoms like oxygen and nitrogen. And so because they're electronegative, if we attach like an oxygen here, that electronegative atom is kind of pulling electrons off of that carbon and removing its shield. So it's being de-shielded is the term for that. And so the magnet will actually kind of affect it more and push it farther downfield. And so if something's on like an oxygen specifically, that tends to show up around 80 or so. Again, this is just approximate. Depending on the rest of the molecule, it can fluctuate exactly where it is, but it'll be kind of in this region. And so again, we're still talking about sp3 carbons, but specifically one that is attached to an oxygen. So again, this carbon is what we're looking at, but it's attached to an oxygen of sorts, right? So that's gonna be like here, around 80, it might be 70, 80, something like that. So it could be like 80, 70 in that region. So another electronegative atom, right? We have nitrogen is another one that could show up here. Those are two common ones you'll see in your structures. And so nitrogen is a little bit less electronegative than oxygen. So it's going to be less de-shielding than oxygen. And so it's still going to be de-shielding, just not as strongly. So you might see that one more around 60 or so. But still it's going to be de-shielded relative to the alkyl region, right? And so what's happening here is that those electronegative atoms de-shield the carbon. Okay, so again, de-shielding is pulling it to the left of the spectrum. All right, so then, so far we've only talked about sp3 carbons. So once we get to an sp2 carbon or even an sp carbon, those are gonna jump pretty far down the spectrum. So those are gonna go above 100. And so this region here, 100 to 150, this is kind of the area where you start getting pi bonded carbons. So you start getting carbons that are double bonded to other carbons. So you get your alkenes in here and you get your aromatics in here. So your aromatic ring carbons will show up in here, right? So all of these guys. So anything that's in a pi bond is gonna show up kind of in this region. And so now we're dealing with sp2 carbons. And sp carbons as well, those will also show up down here, but we don't see those very often, so it's not something we normally have to look for. But they'll also show up down here. And so pi bonds are actually very de-shielding, more so than electronegative atoms. Okay, so that's where you're gonna get your double bonded to C. And then another common piece that we see in our structures is we see the carbonyl bonds. So those are our C's double bonded to O. And these ones, right, they have the pi bond, which is very de-shielding, but they're also bonded to an oxygen atom. So they kind of have a 1-2 punch, right? Pi bond and an oxygen atom. So they're gonna be way downfield. Okay, so those carbons are gonna show up down here in the roughly, 180 to 200 kind of region. Okay, so those ones are pretty distinct because nothing else shows up down here. Those are the only ones that you're gonna see down there. So if you see that, you kind of get the idea that you have a carbonyl. And of course, a lot of this stuff, you're also gonna see similar stuff in your IR. So when you take an IR and an NMR, you can kind of combine the two pieces of evidence to really kind of say what's going on in your structure. Okay, so those are kind of the main regions for that. Okay, so just to kind of sum up the shielding effects. So we learned that Cs are good at shielding. So those would show up, if it's just bonded to carbons and stuff like that, it's gonna be more upfield for sp3 carbons. Electronegative atoms pull electrons and the shielding away from the carbon. And so we call that effect de-shielding, which results in it going more downfield. So de-shielding goes downfield to the left. So again, that's gonna be, for example, that's your oxygen atoms, your nitrogen atoms, halogen atoms. And so again, the more electronegative it is, so oxygen's the most electronegative versus like oxygen, nitrogen, and most of the halogens. So the more electronegative the atom is, the more de-shielding it will be. Okay, and then the last region we kind of talked about are the pi bonds. And so pi bonds are very de-shielding. So those are gonna be the ones that are farthest to the left. Okay, so that's kind of the shielding effects. Okay, so that's kind of talking about the environment. So again, looking at where the chemical shift is, so where the ppm is, tells you kind of this information, kind of what kind of stuff the carbon will be attached to. So there's two other pieces of information that we can get from our carbon NMR. So we'll talk about those. Okay, so the next two, if you look at, again, if you're following along with your handout, we talked about environment. So the next ones we're gonna talk about, I'm gonna talk about these kind of together, but the peak height and the total number of peaks. So we'll talk about those and what they mean about the structures. So I'm gonna kind of discuss them together. And we'll do some examples to kind of sort this out. So again, the number of peaks tells you a lot of information, and the peak height tells you some information about your structure. So as an example, I'm gonna do this structure first, just to kind of explain some stuff with the NMR. And we'll kind of come up and go through what you would expect to see in a carbon-13 NMR for this compound. Okay, so the first one we'll notice is this guy. So this carbon here, I'm just gonna call this carbon 1. And if you read through your handout, you'll see more information about how to number your structure. Normally it's based on your spectrum. So the spectrum, you'll number all the peaks, and then you'll match those numbers to your structure once you have the structure assigned. Here we're kind of going backwards because we're starting with the structure and we're gonna be coming up with the spectra. So I'm just gonna put numbers on here and then we'll just match those with what we draw down below. But anyway, the most downfield peak is gonna be this guy, right? And so carbon 1 here is gonna be way downfield. That's the most downfield you can get, is when you're in a carbonyl carbon, right? So that's the one we would expect to be around 180 to 200 ppm or so. And again, the exact number doesn't really matter, but we do know it's gonna be way downfield, and nothing else shows up down there other than carbonyl carbons for the most part. Okay, so if we're gonna draw kind of a spectrum, right? And we're gonna go from like 200 to 0 ppms. Right, so this guy we'd expect it to be way down here, and the carbon-13 13 NMR spectrum, they're just going to be kind of single peaks that just look like lines. So it's not as interesting as like an IR spectrum. It's just kind of these single peaks. And so this peak here would represent carbon 1. So there's 3 other carbons in this molecule, and each one of these carbons is completely unique, or we call those chemically unique or chemically unequivalent to each other, because this methyl is different than this methyl, right? Because they have different attachments. This methyl is attached to a carbonyl. This methyl is attached to a CH2. This is the only CH2 in the molecule. This is the only carbonyl carbon in the molecule. So each carbon is unique. So each carbon will have its own peak in the carbon NMR. And so if I go through and number these, 2, 3, 4, right? All 3 of these are sp3 carbons. This one, number 1, is the only sp2. So 2, 3, and 4, we'd expect those to be much more upfield in the alkyl region, right? They're not attached to any electronegative atoms. They're not doing anything special, so they can kind of be anywhere between like 10 and 50, depending on how de-shielded they're being. But they're going to be down here in the alkyl region, right? And so there's also just relative effects. So like these ones, carbons 2 and 3, these ones are closer to this carbonyl than carbon 4. So 2 and 3, even though they're not on the carbonyl, they're closer to it. So the closer you get to the electronegative atom, you do sense a little bit of the de-shielding effect, but not very strongly. So these 2 are going to be de-shielded a small bit relative to 4, which is 2 carbons away from that carbonyl. And so 2 and 3, again, all 3 of them are going to be down here somewhere. But 2 and 3 are going to be almost identical. They're going to have very similar shifts. And then carbon 4 is going to be a little bit more upfield from 2 and 3. So you'd expect to see something like that. Okay, and again, 2 and 3 might switch places. That's not the point. The point is that you're seeing 2 peaks and they're roughly in this area, right? So like 2 and 3, we're expecting those to be more downfield than carbon 4. Right, and the reason is because in the structure, those 2 are closer to carbon 1, which is heavily de-shielded. So they're experiencing a little bit of that de-shielding effect relative to 4, which is even farther away. So the farther away you get, the less of that de-shielding effect you're going to feel. Okay, so just to kind of sum up what we're kind of getting from this structure. So if we just looked at the structure, again, just to kind of summarize the structure of this molecule, we'd expect to see 4 different peaks because we have 4 different carbons in this molecule. So 4 different peaks because we saw there's 4 different carbons in that molecule. And then in terms of the peak height, because each of these peaks represents the same number of carbons, so each peak represents 1 carbon, they're all going to be roughly the same height. And that happens when they're all representing the same carbon, or the same number of carbons. So each peak equals just 1 carbon. Okay, and so what we're going to see in our next example, we're going to see an example where the peak heights are different. All right, and it's going to correlate with the number of carbons that it corresponds to. Okay, so I'm going to go on to the next example. Okay, so we're going to do an example that has some symmetry in the molecule so we can get into what happens there in terms of the peak height and the number of peaks. So that first example had no symmetry. So we're going to do an example that has a little bit of symmetry and see how that affects things. Okay, so here's a molecule. So we're going to do this example next. And for this one, we have a set of methyl groups here. So like this methyl and this methyl are equivalent to each other. We say chemically equivalent. And what that means is that all of their connections are identical. So this methyl and this methyl, they're both connected to the same carbon. And then, after that, everything else is the same. So it doesn't matter which one it is, they're identical to each other. And we also have another pair of methyls over here that are chemically equivalent. And it's due to symmetry. It's not the same kind of symmetry like we saw for like a meso compound. It's not always a mirror plane. It can be just a connectional or a constitutional symmetry where they have just all the same connections. They're identical to each other. So like this one, this carbon here, this is going to be the most downfield carbon. So I'm going to call this one carbon 1. And then going away from the bromine, they're going to drop off in their deshielding. So carbon 1 is going to be the most deshielded because it's attached to an electronegative element. And then these two here, right, these two carbons are what we call, the technical term is that they are chemically equivalent. And so again, what that means is they have the same connections throughout the molecule. They're symmetric. They're identical to each other. And so because of that, if we're labeling them with numbers, they would end up with the same number because they're the same carbon. So we'll call that carbon 2, or that's going to, in the NMR, that's going to be peak number 2. And then this one, we'll call that one peak 3. This carbon is unique, so that's going to be peak 4. And then again, we have two that are the same over here, right? These two are chemically equivalent. They're the same, so those would have the same number. That'll be peak 5. So again, what this symmetry is doing is that we have in this molecule, we have 7 carbons, but we're only expecting to get 5 peaks in the NMR because of that symmetry. So the number of peaks doesn't always match the number of carbons if there's symmetry in the molecule. Okay, so let's kind of, again, investigate this NMR. So our ppm scale. All right, and so again, this first one, these are all going to be in the alkyl region down here, kind of 0 to 50, because they're all, well, at least 2, 3, 4, and 5. Those ones are just regular sp3 carbons attached to other sp3 carbons. Carbon 1 will be a little more downfield, but not a lot, because bromine, if you look at it on the periodic table, it's not that electronegative, so it's not as electronegative as, say, a nitrogen or an oxygen. So it's not going to pull it that far. So you're expecting it, again, the rough number is all you're looking for, but you would expect that one to be more downfield relative to the other ones. That's all that you really care about. So carbon 1, peak 1, might be somewhere like around here. And then all the other ones will be more upfield relative to it. Okay, so then we'll just go in this order. So if you look at these, again, carbons 2 and 3 are going to be the next most downfield because they're the next closest. They're all beta carbons to the bromine, right? 1 is the alpha carbon, 2 and 3 are beta carbons. So those would be the next most downfield, and then 4 will be more upfield, and 5 will be the most upfield because they're getting farther and farther away from the bromine. Okay, so anyway, if we have 2 of the same, right, we're gonna have carbons 2 and 3, peak 2 and 3 are gonna be like roughly around here. So I'm gonna put 3 in first, it's gonna be somewhere around here. And then 2 is gonna be right near it. But if you have more than 1 carbon, so here we have 2 carbons that are identical, the peak is gonna be roughly twice as tall. So the peak that represents those 2 carbons is going to be roughly twice as tall. So again, if you have 2 carbons, its peak is going to be twice as tall. All right, and again, that's due to symmetry in the molecule. Right, so that's what's going on here. So this peak right here is twice as tall as 1 and 3 because it's representing twice as many carbons. So these would each be roughly as high as each other, 1 and 3, and then 2 is going to be roughly twice as tall. And it's not going to be exact. The peak heights are not always exact, but they're going to be roughly the same height, or roughly twice as tall. Right, and then we have 4, so then 4 is going to be more upfield than those guys. And it's only 1 carbon, so it's going to have the 1 carbon height. And then carbon, or peak 5, is going to be even more upfield because it's farther away from the bromine. And it's going to be twice as tall as those other ones, so roughly the same height as peak 2. And so you're expecting to see something like that. Right, so again, based on the structure, if we kind of summarize the information we would get from this guy, so I'm going to summarize that below. So even though this structure has 7 carbons, but based on the symmetry, we would only expect 5 peaks. So there's 7 carbons in the formula, but we would expect to only see 5 peaks in the carbon NMR. And that's because it only has 5 different kinds of carbons, right? We'd expect 2 of the peaks to be twice as tall because we have 2 sets of 2 chemically equivalent carbons. In terms of the ppm, the chemical shift, we'd expect all of these carbons to be in the alkyl region. So those are relatively upfield. We don't have any sp2 carbons. We don't have highly electronegative atoms. We're expecting them to kind of all be in the alkyl region. Okay, so I'm going to do another example. And this one is in your practice handout on page 4. So if you go to page 4 of your handout, it's in there. Okay, so it's going to be at the top of that page. And so here we have it in bond line notation. All right, and so here we have some more electronegative atoms than the last one. So like this carbon right here, again, carbonyl, that one's going to be the most downfield. That's going to be in that 180 to 200 region, ppm. And then this guy, this carbon right here, this one's attached directly to an oxygen atom. And so this one we would expect to be the next one. If we're going from downfield to upfield, this one we would hit next. And that's a special region, right? So if we're attached to an oxygen, that's going to be very distinct in the carbon NMR. It's attached to an oxygen, and so that's going to show up in that 70 to 80 ppm region. Right, and again, these are really rough numbers. It can go outside of these regions, but it's going to be kind of in that area. Okay, so that's a really special one because that region, there's nothing else that really shows up there. So that's kind of distinctly an oxygen atom attachment. And then we have these other 2. So these last 2, this one's kind of beta to the oxygen. This one's next to a double bond. Those ones are kind of getting close to some deshielding stuff, but they're just regular alkyl carbons. And so these are going to be in the alkyl region, very upfield in the spectrum. And relative to each other, it would be hard to just randomly kind of predict their placement. So one of these would be peak 3 and one of these would be peak 4. But it would be really hard to predict. So you could kind of assign them either way. So anyway, if we start piecing together the spectrum, so again, 200, 0. Okay, so now we're going to do another example. And this one is also in your practice packet. This one is on page 3 of the practice packet. And so if you look at that one on page 3, it's also giving you the examples of how to tabulate your spectral data. And so this will be more important once we start doing this in lab, but this is also explained in the how to tabulate spectral data handout that is on Canvas. So this is the same example that's in that handout. So anyway, we're gonna go through it and kind of like devise kind of what's going on with the carbon NMR. And so this is our first example where we've seen an aromatic compound. So this aromatic ring is gonna show up in our NMR spectrum, but we have some familiar carbons. So we have this guy here, this is another carbonyl. That's the one that's gonna be way downfield around in the 180 to 200 region. So let me draw our little regions first. And then we have these two here. These are regular alkyl kind of carbons that are gonna be more upfield. And so I'm gonna label those 6 and 7. And we'll see that because these ones, well, once we have the numbers on them, those numbers will make sense as well. Okay, so 1 is gonna be down here, right? Because that one's attached to the carbonyl. And 6 and 7, those are gonna be in the alkyl region. 6 will probably be a little more downfield than 7 just because it's attached, it's near to kind of pi bonds. It's not part of the pi bond, but it's next to them. So we have 6 and 7 are gonna show up somewhere down in the alkyl region, down here. Okay, and again, 6 is gonna be a little more downfield than 7 just because it's in between 2 pi bonds, and this one's next to 1 pi bond. Okay, so then these ones, that brings us to the aromatic ring. And so the aromatic ring in this example has some symmetry to it. And so if you look at it, this carbon and this carbon are unique. So those are gonna have their own shift. And then these 2 carbons are actually the same as each other. So we have a pair of chemically equivalent carbons here and a pair of chemically equivalent carbons here. So these ones are the same, and then these 2 are the same. And so if you look, there's kind of a plane of symmetry going down the molecule here, connection symmetry, right? So these 2 are gonna be equivalent, these 2 are gonna be equivalent. And so if we kind of rank them, if we're going from downfield to upfield, this is gonna be the next one we encounter. So I'm gonna number this one number 2. And the reason for that is because this one, it's on a pi bond. It's part of an aromatic ring. So that's gonna be very de-shielding. So again, our aromatic region is gonna be here, right? So in the 150 to 100 region, that's our kind of aromatic region where you'd see the aromatic carbons. And then in addition to being aromatic, hold on, let me move that up. So that's our aromatic region. In addition to being aromatic, let me zoom out a little bit. It's also attached to an oxygen atom. So the oxygen atom plus it being on a pi bond is gonna pull it downfield within the aromatic region. So we'd expect that carbon 2 to be closer to the downfield side of that region. Okay, and then the other ones, it would be really hard to rank these. So we'd expect 3 more peaks, 1 peak for this one, that set of carbons, 1 peak for this set of carbons, and 1 peak for this carbon. And in terms of predicting them, it would be really hard to kind of predict exactly where they are relative to each other, but we'd expect them to be somewhere in this region. So we would expect to see 2 peaks that are double tall, so twice as tall, and then we'd see 1 shorter peak in that region. So again, how they actually come out, you kind of have to do the NMR and see, but what ends up happening is that this one ends up being the next most downfield, then this one is more upfield, and then this one. And so again, in aromatic rings, it's not as clear. Like usually if it's like an sp3 carbon, it's more clear like, oh, the farther away we get from the electronegative atom, the more upfield it will be. But in an aromatic ring, it's not as clear. There's a lot of stuff going on with the resonance and where the electrons prefer to be. And so it's harder to predict. If it's directly attached to an electronegative atom like this, that's gonna pull it downfield. But for these ones that are just attached to carbons, the relative positioning is gonna be hard to predict. So all you really need to gather from that is what and how many peaks you would see. So again, the point here is that you'd see 3 peaks and you'd see 2 that are twice as tall as this one. And so again, you have the actual spectrum in your handout, but again, what you would predict is to see 2 tall ones and 1 short one, and they're all gonna roughly kind of be in this region, right? And again, you wouldn't expect you to predict like them to be in this order, but that's kind of where you would expect to see them. And the order they're in doesn't matter either. You're just expecting to see 2 tall ones, 1 short one. Okay, so that's kind of for that one. And so I wanted to say a couple more things about the aromatic region, because just looking at this aromatic region, that can tell you a lot about your aromatic ring. And because aromatic rings are so common in organic molecules, that's something that you're gonna see pretty often when we're doing this kind of stuff. So I wanted to spend some time kind of going over the aromatic rings and just giving some examples. Okay, so again, this is just kind of diving in a little bit into the aromatic region specifically. Again, that's roughly 100 to 150 ppm. And so for example, like the one we just did, right? So if we have an aromatic ring that has 2 substituents on it, so 2 things on it, and I'm labeling them R1 and R2 because I'm showing you a situation where the 2 substituents are not equal to each other. So just 2 different things. It doesn't matter what the 2 things are. The point is that they're different. And so if you're looking for symmetry around this ring, the symmetry for this guy is kind of right down the middle, right? Because these carbons on either side are equal to each other because they have the same connections, right? It's a CH in an aromatic ring, right? That's bonded to this carbon. They're both bonded to this carbon, and then they're both bonded to the same stuff on the left side. So this is an example, like the example we just did had this type of symmetry. So you get 1 unique peak here, you get a set of peaks here that are symmetric, you get another set that are symmetric here, and then you have another unique carbon here. So in a situation like this, where you have, again, substituents on opposite sides, and they're different from each other, you would expect to see 4 peaks in the aromatic region for carbon 13 NMR, right? So you'd expect to see 2 shorties, 2 short ones, and then 2 tall ones is what you would see for that kind of pattern. All right, and then so if we had a similar substitution pattern, but both of these are the same, so let's say R1, both of these are the same. So again, it doesn't matter what they are, it just matters that they're the same. Then you have extra symmetry, right? Because you have symmetry here, but you also have symmetry this way. And so you end up with a situation where these 2 carbons here and here are the same as each other. And then you get a situation where now all 4 of these ring carbons are all the same. Right, so there's an additional level of symmetry here. So like for this aromatic ring, you'd expect to only see 2 peaks in the aromatic region, right? With a ratio, right, you'd see 2 to 1, right? Or 4 to 2, right? Because you'd have 4 for this one, and then you'd see 2 for that peak. So the peak height would kind of show that as well. So kind of continuing with that, looking at other just examples of aromatic substitution patterns. Again, here's another example where the 2 substituents are not equal. And so like in this case, because these are not equal, there's actually no symmetry in this aromatic ring, right? Because there's no symmetry because these 2 don't reflect on each other. And so you actually have a situation where now every single carbon is unique on this ring. So like if you take like even these 2, for example, this one is closer to R2, but this one is closer to R1 than the other one. So even though they're very similar, they're not the same. They're not identical. And so if they're not identical, they're not going to have the same shift. They'll be very close to each other in the carbon NMR, but they won't be identical. So you'll actually see two distinct peaks for those. And so all of these all the way around the ring are unique. And so you'd expect to, in the aromatic region, you would expect to see 6 peaks. Again, so I'm not talking about the rest of the molecule, I'm just talking about just the aromatic ring itself, right? If there's more carbons off of these guys, those will have, you know, whatever their peaks are in the NMR. Okay, so I'm gonna do one more aromatic example and then move on from there. So let's say we have that same kind of substitution pattern, but the two substituents are identical, right? So they're both the same. And so again, if they're identical, we have symmetry here. So in this one, we'd have symmetry going kind of down the ring this way, right? Because R1 equals R1. And so this one, right, this would be a unique carbon. So that's 1. And here I'm just giving them random numbers. I'm not like ranking them where they would show up. I'm just putting the same number on the same carbon, right? So like these would be identical to each other. Those would get the same number, same peak. These two are identical to each other, so they'd end up on the same peak. And then this one would be unique, so it would get its own peak. So this is actually very similar to the first example we did. It has a different substitution pattern, but it has similar symmetry. So you'd still expect to see 4 peaks. And then you'd see, you know, a ratio of 1 to 2 to 2 to 1. So you'd see 2 tall peaks and 2 short peaks in that one as well. Okay, so before we go on to HNMR, I did want to cover just a couple things to kind of cover stuff that you might see in some of your NMR problems. And these things are going to apply to kind of both carbon and HNMR. And so in your lab that you're going to be doing this week, you'll be running your NMR neat, which means it's not dissolved in anything, it's just plain substance. But a lot of times NMR is often run as a solution. So instead of just being your compound that you're studying by itself, they actually dissolve it in a solvent. And so as a result, dissolved in a solvent. So as a result, you can actually sometimes see peaks that result from the solvent being in the NMR as well, because the solvent is another organic molecule that you can see sometimes. And it's not going to be as big of a deal because we use these solvents that we call deuterated solvents. Deuterated solvents. And so what that means, a deuterated solvent is a solvent where the H's have been replaced with deuterium. And so deuterium, the symbol for deuterium is capital D, and that's not an element on its own. You won't find D on the periodic table. That's an isotope of hydrogen. And so regular hydrogen is, if you write the nuclear symbol, the nuclide symbol for hydrogen, it's just H1. And again, this is the mass number. So normal hydrogen just has a mass of 1 because it's just a proton, that's all it is. Right? And so that's kind of what H1 is. That's what we're referring to as a proton sometimes, because it's just a proton in the hydrogen nucleus. But what deuterium is an isotope. And if you recall what isotopes are, it's an atom that has a different number of neutrons, but it's the same element. And so deuterium is actually hydrogen with a mass of 2. So it has 1 proton and now it has 1 neutron. So it has double the mass. And what happens is that this one when you replace stuff with H2, we also, again, use the symbol D instead of writing H2. These don't show up in the H NMR. So we're going to talk about H1 NMR next, but it's important to know that if you use a solvent, right, those deuteriums don't show up. However, the C's show up a little bit. Because there's still carbons in some of the solvents that we use. So sometimes you'll see those in your NMR. Okay, so not all the time, but sometimes. And so what that looks like is you'll see just kind of extra peaks in there that don't belong to your compound. And so for an example of this, look at the lab slides on Canvas for this experiment. So I think slide number 2 has an example. Oh, let me move this up. So slide number 2 in the lab slides, they're on Canvas now for this experiment. It has an example of a carbon NMR and it shows you what it looks like to see that extra, for that one, it's showing you one of the deuterated solvents. And so different deuterated solvents that are used, there's a lot of different ones, but these are just some common ones I'm going to talk about. So like, for example, a common NMR solvent is, this one's called chloroform or trichloromethane. You'll see that one a lot. And if you deuterate it, what we do is, again, we're taking the H's and we're replacing it with deuterium. So you'll see this, it's CdCl3. And so we call it deuterated chloroform. You can do this with water. So you can make deuterated water, D2O. That's another common NMR solvent. Or sometimes you'll see things like acetone. So acetone actually has this structure. And it has 6 hydrogens coming off of those carbons. And so if you deuterate it, right, we're just replacing all of those hydrogens with deuterium atoms. So it's a different compound because it's an isotope with different isotopes for the hydrogens. Okay, so again, the one in the slide, it's showing us an example of a compound dissolved in deuterated chloroform, and it's showing you where those peaks show up. So like in a problem or something, I would have these labeled, so they would be labeled and told to you that they are the solvent peaks. But if you see weird little peaks that are like much smaller usually than your actual compound peaks, those are usually resultant from one of these solvents that have carbons in them. D2O, of course, doesn't have any carbons, so this one wouldn't show up in the carbon NMR. But this one gives you some weird peaks around 70, and then this one, of course, would give you some peaks as well. So if those are in the spectrum, they'll be labeled, and I'll tell you that they're solvent, and you would just ignore those. So you just would not pay attention to them. You just cross it out and be like, oh, those are solvent. Ignore. Okay, the other thing that can show up, and you're going to see this also in the proton NMR, the H1 NMR, is a compound called TMS. So TMS is what we call it, but what that stands for is tetramethylsilane. And so that's the TMS. And so what it is, it's a compound that we use for NMR to kind of get the magnet to orient itself. Because when you stick these samples in the NMR, the NMR spectra is on a scale of ppm, but the spectrometer itself doesn't know where to set the 0 point. So it might give you all the peaks you're expecting to see, but it doesn't know what number to put them on because it has no idea what they are. It just knows where they are relative to each other. So in order to get the computer and the spectrometer to kind of orient where the numbers should go, we actually add this compound to our solution and use it as an orientation point because it has a known ppm. And then we can kind of tell the computer this one should be here. And then it kind of orients everything else. So anyway, this is used in both carbon and H NMR. So we're going to talk about, again, H NMR next. But in both of those spectra, it actually shows up at 0 ppm. So like this carbon will show up at 0 ppm in the carbon NMR. this H will show up at 0 ppm in the H NMR. So you'll see a peak there sometimes. It's not always there because we don't always use it in all of the spectra that we take. But a lot of them you'll see a weird peak just at 0 ppm. And that's a peak you can just ignore. It's not part of your compound. It just belongs to this guy. And the reason, this is very, very upfield, right? And the reason is it's on this giant silicon atom. And a silicon atom, in terms of shielding, is like a super shield. And so if you have a carbon attached to a silicon, it usually almost always ends up near 0 because it's super shielding it from the magnet. It doesn't get pushed downfield at all. Okay, so what you can take away from that is that you just need to ignore this peak. Okay, so those are examples. So the solvents and the TMS, those are things that can show up in your NMR that you would just ignore. They're not part of your compound. Okay, so that's it for carbon NMR and just like a couple extra things. Again, for some just quick practice, you can do the practice problems in the slides that I posted online, the NMR lecture slides. And then there's also, of course, problems in your practice packet to do. So I'm going to stop the video here, and then the next video will cover HNMR.